Hello. Hello. Yeah. Am I audible? Hello.
Yes, you're audible.
Yeah. Let the others join. So that I think this was one of the problems someone asked last time. So we'll start off with this and we'll do some problems because what I felt after looking at some of your copies is that we need some practice, I guess. So we'll do some basic problems first, like some famous problems, and then we'll move on to some difficult ones or some lesser known problems. Say, yeah.
Will this be the last class on number theory?
What? This would be the last class on number theory. Yeah. The next two classes that I will take would be on combinatorics, and yeah.
Will there be classes for geometry as well, or just number theory can be algebra and calculus?
Yeah. So like in combinatorics, I'll try to like wrap most of the things up in one class if I can. If I'm able to do that, then I'll start off with some geometry.
Thank you.
Yeah. So like this is a very limited amount of time, right? So I have sent you guys some theorems. So, but I think there are some theorems there which need some more explanations, right? So, yeah. So, but most of the basic ones are covered there. So, yeah. So let's start off with this problem today. So 6 people have come here. So yeah, since it's being recorded, so let's start off with the class today now. So the problem is let a, m, and n be positive integers. We need to prove that GCD of a to the power of m minus 1, comma a to the power of n minus 1 is a to the power of GCD of mn minus 1, right? So now let's first check why would this be true, right? Like this looks like a good form, but why should this be true, right? So what can you what can you say about this?
What about a equal to 1? What happens then?
Yeah, obviously I'm talking about like these things should be positive, right? Otherwise there's no meaning. I mean, like GCD of 0 comma 0 is 0. Yeah, that is fine, right?
When we consider GCDs, we assume that at least one of them is nonzero.
Yeah, so like I mean, yeah, so that those are trivial things. Like let's go into the like why is this true in general, right? So what can you say about this thing? Like this is of the form a to the power of d plus minus 1, right? If you take let's take uh, GCD of m comma n say d, right? So and yeah, we at least take d to be 1, right? Otherwise there's no point. So okay, so now if this is the GCD, so what is this claiming? This is the GCD of a to the power of m minus 1 and a to the power of n minus 1. So this implies what? This implies a to the power of d minus 1 should divide a to the power of m minus 1, and it should also divide it, a to the power of n minus 1, right? Right?
Yeah.
Now, intuitively, this is correct, right? So intuitively, this formula should be correct, right? Because like if d is the GCD of m and n, then it is dividing both of them. But we are not sure exactly about why it should be the GCD, but it divides, right? If d is the GCD of m and n, so this two would satisfy, right? So now in the last class I told like we can approach it in many ways, right? But like this is a one liner if you know Fermat's theorem, right? So but let's assume we don't know anything, we just know Euclid's algorithm, right? So what happens then? So okay, so let's take something like, right, like these two are symmetric, so we can take so this, right? So now what can we say, like okay, let us name this as suppose the GCD as G, right? and we have written this GCD of M and N as D, right? So we know that, okay, so let me claim this. So GCD of A comma B is equal to GCD of A minus B comma B. So is this claim correct?
Yeah.
And you understand that this is the claim that we use while we do this, like for example 79, say 41, so
Yeah,
one.
absolutely.
So this is the thing that we use, right? So A minus KB and B would have the same GCD when this is positive. So I'm taking only the valid cases here, right? So this is fine. So okay, so and in specifically in Euclid's algorithm, we don't take this to be we don't subtract just once, we subtract it the most number of times that we can, right? But let's go with one here, right? Like one step. So I took G as the GCD, right? So G is the GCD of so this would be equal to the GCD of what? A to the power of M minus 1 minus a to the power of n plus 1, like subtracting, minus a to the power n minus 1. And we took m greater than equal to n, right? Like the other case is symmetric, right? So this is basically what? This is basically GCD of a to the power of m minus n minus 1 comma a to the power of n minus 1, right? Is this clear? Like I'm just taking out a to the power n outside, right? So a to the power n is not like this. A to the power n is co-prime to this. So let me rewrite this step. So GCD of right now a to the power n and a to the power of n minus 1 and a to the power of m minus n minus 1. These have GCD 1, like this two and these two have GCD 1. So a to the power n goes out, right? So the a to the power n doesn't matter when I'm calculating the GCD of these. So the GCD of this would be equal to the GCD of this, right? So essentially what I'm only using is the things that I used in first class, that I told in first class, right? So what did we get? So we got GCD of a to the power of m minus 1 and GCD of a to the power of n minus 1. This is equal to GCD of a to the power of m minus n minus 1 and a to the power of n minus 1, right? So now basically we are approaching what Euclid did, right? What Euclid did basically, Euclid checked whether this is greater than equal to 0 or not. And if this is greater than equal to 0 and it is also greater than equal to n, then we can subtract n once more, right? So we can write this is equal to, if this is true, then we can write GCD of, just a sec, let me get it here. So we can write GCD of a to the power of m minus n minus 1 comma a to the power of n minus 1. This is equal to GCD of a to the power of n minus 2n minus 1 a to the power of n minus, right? And we can go on like this. So what is this basically? So this is Euclid's algorithm running in powers, right? Right.
Right.
So in the end, what would be left here, like in the power? So in the power, what is happening? In the power, we are getting things like m minus n, m minus 2n, and so on. So essentially, in the end, we would get something similar what we get in Euclid's algorithm, right? So G would be equal to a to the power of m, like these uh, these things will go on till I can reach the point where it's getting divided, right? So what would be that point? That would be nothing but GCD of M and N. And this is a way of writing GCD, right? So like when I'm talking in number theory, this denotes the GCD of A and B. Okay, so I am not writing explicitly GCD every time. Okay, so this should be what? So the value should be this, right? I'm writing it once again. So for right, like -1 by in outside. So yes, and can anyone give me a quick proof of this using Fermat's theorem? Like, yeah, is this part clear?
Actually, I wanted to ask if we keep going in that sequence, then we'll have m minus n, m minus 2n, and eventually m minus qn for some integer q, positive integer. So, like Bezos identity.
Okay. Just let me write this down, and you will, I guess, you will answer this for yourself. So, say for this, right? What happens? I am multiplying 2, right? So, just a sec. Right? Now, what do you do?
Yeah, now I take the 41 and get it divided by 5.
Yeah. So, how does it translate here? Like, so I'm going on like this: m minus n, m minus 2n, and so on. So, suppose I reach a point where, so okay, I understand what your doubt is. So say I reach a point where this is greater than 0 and m minus n is less than n. Then what do I do? So I was talking about this, right? So I do this when this happens. Now, what happens when this happens? Say for some k. K.
Okay, maybe at that point I do the reverse, like what I did with a m minus 1, I subtracted a to the power m minus 1 by a to the power n minus 1. Now I subtract a n minus 1 with a to the power m minus k n minus 1.
Yes, exactly. So basically, what this thing implies is, like I'm talking about the linear one. So the GCD of these two is equal to what? The GCD of these two, right?
Yeah, right. Then I flip the sides. Right?
Yeah, exactly. So when this situation happens, you're basically back to square one. So
Yeah, right.
you go on till you reach this point. Like, and why you will reach that point? Because it is basically Euclid's algorithm, right?
Yeah.
Okay. So now, can you give me a quick proof using Fermat's theorem? Why this should be true? Or Euler's theorem, maybe, because it's very general here. So Euler's theorem. Like, do you guys know this? Otherwise, I will skip this. Like, a to the power of phi n is congruent to what mod n? Like,
Yeah, 1. Right.
is it 1?
I guess so.
Okay. Why is it 1? Like, you don't need to guess. Like, this is true for primes. Like, this is what Fermat says, right? Like, this is Fermat's theorem, right?
Yeah.
And so this is basically a general form of Euler's theorem. Euler's theorem says a to the power phi of n is congruent to 1 mod n, right? Okay. So like, so can you see why this, how you can approach this using this? Okay, think about it. We'll come back to this later on, maybe. Like one more proof, how, I mean, a very quick proof why this should be true. Okay, so now let's go to this problem. So let m and n be positive integers such that GCD of m and n and LCM of m and n are defined like this. Like, so this is say D, and this is the L. So GCD of M and N plus LCM of M and N is M plus N. Show that one of the two numbers is divisible by the other. So let's take the GCD of M and N.
Could you wait for a minute? I want to try.
Yeah. I'm just writing it down my notations. So if you try, just use my notation. So it might be easier for me to keep track of it. So these two are the things that I'm using, say, suppose. You need to, denote this with something, right? So yeah, and keep in mind the problems that we'll be discussing. Every problem will have a, underlying thing that I want you to understand. So like this also has a underlying like motivation which you might keep in mind.
Will the positive integers m and n eventually be equal?
Yeah, and why? Like this is a very simple problem. So I want you to be very certain about what you are saying. So yeah, it should be equal. Why?
Yeah, okay. So we have taken the GCD of m and n to be equal to D.
Yeah.
So we can write m to be equal to m is equal to D times some m1.
D times some
m1.
okay M1.
Just take some positive integer
Yeah.
m1, and
Yeah.
n can be written as D times some n1.
N, right? So n
Yep.
can be written as D times some n1. Yes, and
We know that the GCD of m1 comma n1 is equal to 1.
M1 comma n1 is equal to 1. Yeah.
Because
So,
D is their GCD, so they should be taken.
Yeah. So this is 1.
Now we'll look at the equation that is given. We can rewrite that as D plus D m1 n1 equals D m1 plus D n1.
D plus D m1 n1. You're
Yep.
saying. Shouldn't this okay. Go on. I'll
Equals
and
D m1 plus D n1. Now we can just cancel D out.
just yeah.
And so from here we can say that m1 will divide 1 and n1 will also divide 1. So m1 equals n1 is equals 1.
So like this is a very very well known factorization. Yes. Like take all of
Okay.
them.
I missed something. I missed a simple thing out. Yeah, it's just m1 minus 1 times n1 minus 1, I guess, if I'm not wrong.
Yeah.
Yeah, so we'll just have either m1 equals 1 or n1 equals 1.
Implies what?
So at least one of them is just equal to D.
Yeah. So
And
GCD
the other one is just D times something.
equal to
And
M
we are done.
or N. Right. Like whichever is smaller.
Yep.
So let's go to the next one then. So if P is an odd prime, and A and B are co-prime integers, show that GCD of A to the power of P plus B to the power of P divided by A plus B. Just a sec. Like, yeah. And this is a comma. GCD of this and A plus B is either 1 or P. Either 1 or P. This means either. So I think you guys know this, right? So this means a singleton set notation. So this includes only the points 1 and P if I'm using second brackets. So okay.
call the GCD D so and replace A by minus B modulo D.
Without using modulos, say, like don't use modulos, just use GCDs. We'll come to modulos. Like just use this thing. Like why I'm saying this is like it would be better if you write like the solutions which you can without using the modulo notation, because the professors here at ISI, they might ask you in like some stuff on those during the vivas. So I mean, if you can answer it using a simpler method, try that. So just, I mean, yeah, I understand what you are going for. Try to
There
go.
won't be a Viva this time, actually.
Oh, there won't be a viva.
Yeah,
So-
they issued a notice.
Oh, okay. So that's nice then. Like,
But I mean, if they deduct marks, we won't be even able to know. So yeah, that's risky.
yeah, like if you are sure about a question and like if you know the solution correctly, if you feel your solution is correct, just like make sure that you don't lose any marks for that particular question before attempting any other question, right? So yeah, just okay. So how do we use this? Like try to use this expression like a to the power of, like the previous problem why I gave this one is like you should keep in mind whenever you are given a problem involving GCD and LCM, just try to bring it down to one of them, like either GCD or LCM, both of them would work. So that's the underlying thing. And in this one, what I wanted you to see is this factorization basically. So like using this should be very simple, right?
I do not think the factorization is correct. I think it was this factorization is for minus, not plus.
Yeah, the signs will be alternating.
Yes.
Yeah. So this should be minus, right? Yeah. That's it. Yeah. Now this is correct, right? The last term would be positive, right? This term would be positive, right?
Yeah, so the minus sign comes with the odd power of
Powers, yeah.
minus one is given.
So yeah, so just like this should be a one-liner. So what can you say about this RHS? So the thing is, like, if you can find a factor of a plus b here, and if you can find something remaining, you can say that if this has to divide, then it has to divide the other remaining part also, right?
Can we pair it up in powers of, so like similar powers of A and B? Will that help? I don't know.
Like what I'm saying is, suppose you can take out a factor of a plus b out from here, and you have to add or subtract some terms, so you get something like this. So if you know that this is a smaller term, then you have much more options, right? So what happens, like what is the closest thing that you can get while multiplying with this? So what happens, so like this is a like pretty well-known identity, I guess. Just check whether I'm writing the signs correctly or not.
Instead, okay. Hold on.
Yeah, I'll take the alternative solutions just a bit. Just wait a bit. right? And what would be the remaining term, right? Like keep this factorization in mind. Like I talked about the Vieta jumping problem last class, right? So the Vieta jumping problem also uses a similar technique. So now a plus b divides this thing, right? So if the GC if you have to have the GCD, so what does this mean? So GCD of a to the power of p plus b. So what would this be equal to? This thing, right? Now, what can you say about this? A and B were co-prime, right? So a plus b and b to the power of p minus 1, these are co-prime, right? So the GCD can either be p or 1, right? Yeah. So now someone was giving a solution using modulos. So go ahead now.
I was giving a solution, but it did not involve modulus.
Yeah, go ahead. Yeah, go ahead.
Okay, so I am thinking about using the what do you call it? The property of GCD that you can subtract a factor of the right side from the left side, like that.
Okay.
Suppose you multiply the right side by a to the power of p minus 2 and subtract it from the left side.
Just a sec. So you are using this, right?
Yeah, no, I'm using the the long form.
This form.
No, the AP 8 to the power of p minus 1 minus 8 to the power of p minus 2 p.
Yeah. Just a sec. Let me write it down here again. Right. Yeah. Now go ahead.
Now you subtract from this a to the power of p minus 2 into a plus b.
What I subtract? A to
A
the
to
power
the
of?
power of p minus 2
Yeah.
into whole into a plus b.
Okay.
So what like this is obviously subtracting a factor of a plus b. So the GCD does not change.
Yes. Yes.
So a to the power of p minus 1 is gone. First term is gone, and second term is minus 2 into second term.
Yeah. So these two terms are gone. So
No, the
the second
second
term
term,
remains.
but it's multiplied by 2.
Yeah. Right.
And so forth. Now I am now same thing. I will do same thing. I'll add 3. I will add 2 into a to the power of p minus 3 into b.
Yeah. I understand what you're going for. So yeah. So do the others see what he's trying to do? So he's trying to get back here, right? So is this fine? Right. So this is a shorter way. Okay. So let's move ahead. So let n and p be positive integers and let p be a prime. Given that
So-
n divides, yeah,
Sir, if we simply put a equals to minus b
yeah,
and then
that's
adjust to get 0, we're directly getting p b to the power p minus 1. If we put a equals to minus b.
yes, but
That would be manually doing remainder theorem.
yes,
Yeah.
like that is not exactly the proof, right? I mean, that's where the idea comes, right? That's where the idea comes from. Like you can use this, but like you cannot write that down exactly as a proof, what you are saying, right? Like you need to complete the argument.
Because we are dividing by a plus b.
Yeah.
So we can write a equals to minus b, then we'll get some remainder.
Mm,
Sir, actually, like I think the proof will be complete if we state the properties of the modulo.
could you repeat? I couldn't get what you said.
If we state the properties of the modulo operation, we can complete the proof. We can make it rigorous.
Yes, yes. Like you need to completely state what you mean by like why you can put minus b in place of a, say, right?
Yes, sir.
Yeah. So like that is what I would recommend you do in your rough work, and I do not recommend you write that in your copy, right? Like you understand the easier, like this is the longer version than what you are saying, right? So that's why you want to write it down using the remainder theorem only. But I mean, this would take only 2 or 3 lines. So I would recommend that you go for this longer method, like this one or even the one that Ryan said. But don't, I mean, just don't directly apply modulos and stuff. I mean, if all the people solve that problem correctly, then you will get lower marks. So that's what happens. So okay, so let's go to this problem. So let n and p be greater than 1. So yeah, and was that clear? Like if most of the people can do the problem correctly, then try to go for the easiest solution. And if you think that the problem is very hard, then you can write anything. Like you can apply modulos and stuff, whatever you want. Like even the Chinese remainder theorem. If you are certain that this is not what you feel like if you are certain that it requires difficult techniques, otherwise they will feel like you are trying to use heavy machinery to do some easy stuff, so they don't like that. So yeah, okay, so this problem says that let np be greater than 1. They are positive integers. Let p be a prime given that n divides p minus 1 and p divides n cube minus 1. Prove that 4p minus 3 is a perfect square. So I'll give a hint, like try to give a bound on this n somehow, right? So n divides p minus 1. That's the first thing that's given, right? So from here, what can you say? Like the was the
n
most
is less than equal to p minus 1.
yes, and also what can you say? Like p is a multiple of, like p is like this form, right? P is of the form nk plus 1. So this is the form of prime you are working with, right? So okay, like this is the most that we can do from the first one, right? Like almost. So what can you conquer from the second one condition? Like p divides n cube minus 1. So like what, like the first basic thing is to break this up, right? So okay, so now what? This implies what? P divides n minus 1 or p divides n square plus n plus 1, right? Now why is this true? Like when can I say that this either divides this or this? When these are co-prime,
So
right?
prime. So
These are when these are co-prime and this is a prime.
no, they don't necessarily need to be co-prime. You are just dividing by a prime, right? So
No, I'm not
like
this for this particular case, this is for a prime. Say like I have this. I'm not entirely sure about A. Say like say if A is
Yeah,
not
in that case, they have to be co-prime. But if
yes.
we're dealing with the prime, then we can say that.
Yes. So in this particular case, what is the are these two co-prime always or not? What can you say about n minus 1 and n square plus n plus 1? Like P is a prime, so that's why you can say that P either divides this or this. But like you can like I cannot say or, right? I can say and or. You see what I'm saying?
Yeah, yeah, they will be co-prime.
Yeah. Like you see my point, right? So P divides the whole thing. So P square might also divide the whole thing, right? So P might divide both of them.
Yeah, we can say or but not XOR, I believe.
Okay.
I mean XOR.
Could you repeat once?
I mean, I think we can say or, but not necessarily XOR, like XOR.
Yeah. Right. So okay. Now this one of this thing is absurd. One of these is absurd, right? So this is absurd because we have this, right?
Right.
So this is the only possibility, right? So my previous claim was also false. Like here, this cannot divide this. So I am only left with this n square plus n plus 1. Okay. So this condition is giving us P divides n square plus n plus 1. Okay. That's a start. So what can we say after that? So the first basic thing is this, right? Now, from the first one, we have this, right? P has a certain form, nk plus 1. So we know that nk plus 1 divides n square plus n plus 1. From here, what can we say? So just look at this, n square plus n plus 1. So if A and B are like, if A divides, okay, so A divides B, A divides KB, A divides KB minus, just a second. Yeah, so A divides B and A divides KB, right? So from here, what can we say, right? Multiply with K. So we have Kn square plus Kn plus K this is getting divided by nk plus 1, right? Since this is the multiple of n square plus n plus 1.
Yeah.
So I mean, can't you guys see from here why we are almost done? So what can we subtract from here? Like, what do we want ultimately? We want to prove that 4p minus 3 is the perfect square, right? So let me write it down in a clear format. So nk plus 1 divides k square n, sorry, kn square, right? Kn square plus kn plus k. Now, this implies this, right? right? So I'm just subtracting this basically. This from k times n square plus n plus 1 minus this. So since nk plus 1 divides this and this both, so nk plus 1 must divide the difference of those two, right? So this is basically this, right? So nk plus 1 divides k minus 1 times n plus k, right? Right? So what this gives us? This gives us nk plus 1 is less than equal to k minus 1 times n plus k, right? So right? So let's go back and see what this means. So we got n plus 1 less than equal to k, right? So what does this mean? So we had this, right? P is equal to nk plus 1, and we got n plus 1 less than equal to k. We want to infer about 4p minus 3. So we should convert everything back to p, right? So that we can understand what happens with p, right? So okay. So now can you see is this clear up, everyone? Is this clear up to this? Hello?
Yeah.
Yeah. So what can you say from here? Any ideas, anyone? Otherwise, I'll proceed with the solution. Right? 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 So what do you have essentially? right? So what is 4p minus 3? Right? Is this clear? Or is there any doubt? So a quick synopsis, what just happened. So n divides p minus 1. This gives us p's of the form nk plus 1, right? And p divides nq minus 1. This gives us p divides n square plus n plus 1. Now, if you just plug this in and check all the inequalities, you will see what? You will see that p is greater than equal to n square plus n plus 1. Combining these two, we can say p is equal to n square plus 2n, n square plus n plus 1. Right? Okay. Just a sec. So is this clear, everyone? So I'll proceed with the next problem. Yeah. So are there three distinct prime numbers a, b, and c which satisfies these three equations? That a divides bc plus b plus c, b divides ca plus c plus a, and c divides ab plus a plus b. So the last problem was about inequalities and bounding. Using divisibility. This one was just this basic identity. Okay. So what about this one? So the idea is to bound it again. So do you guys want to try this for 5 minutes?
Yeah, please.
Yeah, so the previous ones were not that much difficult. So that's why I sprinted through those problems. Now I'll slow down a bit, and like these problems would be applications of what we did previously. And if you guys know Fermat's theorem and stuff like that, it would be helpful any day. Yeah. So, okay. So try this one. And also if someone is interested, so these two are the problems that we'll be doing at least till now. That's the plan. And if we are able to solve these two, then we'll move forward. So, okay. This says if ABCD are pairwise distinct positive integers such that this whole thing is an integer, prove that a plus b plus c plus d is not a prime number. So these two are the problems that we'll be looking at. So I'll give you guys 10 minutes, say, to attempt. Right? So which one do you guys want to attempt first? Just tell me, then I'll just start off with that one.
This one.
Okay,
I mean, for
fine.
me, I mean, ask others.
So, yeah, I think this one would be better because like this is very similar to what we did just the previous problem. Like the previous problem. Not very similar, like the technique is similar. So yeah, okay. And I saw that some of you guys didn't attempt today's paper, so I would like you guys to attempt today's paper, like the mock test, and I mean you can submit it later on also. So like it contains some good problems, so just try those out. Some I got some answer scripts which were which mentioned some really cool solutions. So like you guys should try that one out. It doesn't contain much calculus. I think it doesn't contain any calculus at all, but the other problems are a good collection. So you should try this mock test out, like the mock test 4.
There is observation.
Yeah, did you say something? Hello?
Yeah, there is. I got an observation that
Yeah.
all of ABC, all of them of ABC divides A plus 1 into B plus 1 into C plus 1 minus 1.
Okay.
So their LCM also divides that,
Okay.
and their LCM is just ABC because all of them are primes. So their average GCD is 1.
Okay. Then
And now we expand A plus 1 into B plus 1 into C plus 1 minus 1. So it is
okay, so yeah, you are going in the correct direction. So let me write it down for the others and think for like
and now
give me the answer then.
the LHS is a bigger quantity and RHS becomes a smaller quantity. So you can use inequality based approach.
Yeah, so give me the solutions, like what are the primes?
Yeah, I'm working on that.
Yeah, okay. So what he was saying is okay, so I'll let you guys prove it. So I think this is a good exercise. So what he's claiming is I should write that down at least. So he's claiming this, right? Right? You're saying something like this?
Yeah.
Now
I have an observation.
he is also claiming this, right?
Yeah.
And now why is this true?
Because ABC are primes, so their LCM also divides them. LCM is ABC.
Yes, correct. So this would not be the case, right? In general. Okay. So ABC divides this. That's correct. Now what can we say?
We can say that LCM divides that.
So just let me write this down. So ABC divides this, right? AB plus BC plus CA plus A plus B plus C, something like this, right? Okay. Now,
So the RHS is greater than ABC. So AB plus BC plus CA plus A plus B plus C greater than or equal to ABC.
right?
And we divide by ABC.
Yes. Okay. So K is
And we
equal
can
to,
assume without loss of generality that A less than equal to B less than equal to C.
yes. Okay. Then,
And we replace all denominator BC terms by A. So it comes 3 by A square plus 3 by A. And that is greater than equal to 1.
so he's replacing this, right? We can replace this because this is a very symmetric case, symmetric over A, B, and C, right? So, and this is greater than 1. Why? Why this is greater than equal to 1?
Because ABC divides that, and we divide by ABC. So as ABC divides that, that quantity must be greater than equal to ABC.
So this is equal to K, right?
And
Like,
K should be greater than 1.
yeah. So like
It's an integer.
using my notation, so this is okay. 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 So now we have what? We have been given that ABC are all primes, right?
And A square greater than A. So 3 by A square less than 3 by A. So A less than 6, and we can check out case works.
Yes.
Case by case.
Yes. And why is A less than 6? Just give me an argument for that.
Because A square greater than A. So 3 by A square less than 3 by A. So 6 by A greater than 1.
Okay, what happens for 5?
I said we can check cases A equal to 2, 3, 5.
Yeah. Okay. So okay, fine. But like the upper limit should be 4, right? Like you need to check only below 4. Okay, so like so after this point, this is casework, and what I was saying is you need to check only A, 2, and 3. You don't need to check 5. So just check why I'm saying that. Okay. So after this is just casework, right? So what about the case for A equals to? Then we have what? Right? So from here you can argue that right. So
And again, inequality based approach works.
Okay, so this is fine. So this is a pretty common problem. So let me give you something interesting then. Okay. Just wait for it. Okay, so let's try a bit something bit different. Okay. Let's try this. Let a1, a2 dot 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 an be n distinct positive integers. Be n distinct positive odd integers. Suppose the differences ai minus aj are all distinct. For all I and j, right? Prove that a1 plus a2 plus dot 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 up to an is greater than equal to n into n square plus 2 divided by 3. So is the problem clear? Yeah, is the problem clear? Also, let me write down one more problem. Show that there are infinitely many points on the unit circle such that the distance between any two of them is a rational number. you guys had polynomial classes, right? Hello?
Yes.
Yeah, so just one more problem from polynomials, because yeah, so the previous problems that I was giving was from a book called I am not so sure about the book's name, but it's a popular book on number theory. So I think most of you might have seen those problems earlier. So these are some problems which you might not have seen. So let's try these. Okay.
What was the name of the book?
I'll send you guys a PDF of the book. I have named it according to I mean, I had that book downloaded while I was preparing myself. So the book's name is number theory _ text that I saved. So I can send you guys that file. So yeah, I'm not exactly sure. I mean, it doesn't have a cover page. So it was on AOPS, I guess, when I was a user there. So yeah. So just try these two, and I'll give one more. So these problems are from our regular classes. So real coefficients satisfying. So which is 1 less than equal to 1 for x lying between -1 and 1. So find the maximum possible values of b. Find the maximum possible values of b and give a polynomial attaining the maximum, and give an example. Of a polynomial attaining the maximum. Yeah. Okay. And have you guys heard this problem? So this is also like the next one is also a pretty known problem, but if you guys have not heard it before, so I think you should at least have, I mean, you should at least know once. Suppose I have a polynomial. Suppose I have a polynomial with positive integer coefficients. Say f of x equal to f naught plus x1 plus dot, dot, dot. And these are all positive integers, positive non-negative integers. So okay, so okay, so say one of you guess a polynomial. I mean, like think of a polynomial with positive integers as coefficients. So think of a polynomial, I mean, pretty small degree, say, suppose, for your ease of access, ease of calculation. So someone of you, like, give me a polynomial. Like, don't tell me the polynomial. So Ritobroto, say. So think of a polynomial. Now, my question would be like, if, okay, so let me erase this. Suppose okay. Now, okay. So now say the question is like this. I can ask questions like, what is f of a, where I give a of my own choice. Ritobroto has to answer the value, right? So f of a. So I give him a and he gives me back f of a. So what is the maximum number of questions that I need to ask in order to know the polynomial that he is thinking of?
Maximum or minimum?
Oh, sorry, minimum. Minimum, yeah. Yeah, so I mean, give me a like any one of you, just think, I mean, who wants to volunteer? Just someone volunteer. Like, think a polynomial and let me ask you this. What is f of, say, what is f of 1, say?
Three.
1 sec. Okay, so f of 1 is 3, right? You were saying f of 1 is 3. Okay, so give me f of 10.
$111.
Okay, so just a sec. My claim is this is enough. So can you, can anyone else guess the function from here?
Well, it looks like he had the polynomial x squared plus x plus 1.
Yeah, it's the base 10 expression of the coefficients.
And now why is this working? Okay, so now your turn. I am thinking of a polynomial. You ask me a question. So ask me something.
F1
So f1 is 111.
and F10.
F10 is also 111.
Sir, I would ask F1 and and then some F greater than 1. Sorry, some number greater than F1.
Yeah, and why should we take something greater than f of 1?
Because then then the base trick can be used, because if
What is the trick essentially? Yeah, that's what I'm asking. What is the trick that I'm using here?
what is trick is
Expand F10 in base 10, and we have F10 is the power of 10s in.
No,
If
no,
we-
no. Like when f1 is 111 and f10 is also 111. So how can you say then? Like you asked me f of 1 I gave you 111. So you then ask,
The polynomial was given with positive integer coefficients. How can they be equal? The function should be strictly increasing or non-decreasing.
like, what if like it is a degree 10 polynomial? It can have equal values at 10 points, right?
But it is with positive integer coefficients. So if we take x to be positive, the function increases, right?
Yes, but what if f0 is 111 itself?
I think he is right. How can the number not change?
No, like, what if f0 is 111 and the 10th power is only f0 is 111? Say,
Yes, in that case, f needs to be a constant function. I mean, if it is not increasing at all.
Exactly.
so essentially, what is the thing that we are using? What is the base trick? That's what I'm asking. Like, why we should take something greater than f of 1?
If I take something something greater than f of 1, I am taking something greater than each of the coefficients. So I can use the base trick.
So f of 1 is sum of all the coefficients, right?
So can you hear me? What I
Yeah.
said?
Yeah. So f of 1 is sum of all the coefficients, right?
Yes. So
So
if
you
I
are taking something larger than the largest coefficient.
yes.
So if you can take something larger than the largest coefficient, you are done. So like anything larger than the largest coefficient works. I'm working with powers of 10. Why? Because if you are working with powers of 10, then you can basically see the whole polynomial itself.
Yeah, but power of 10 is not necessary, right?
Power of 10 would be very easy, right? Otherwise, power of 2s would be very difficult. Like for example, what if something like this, right? Say I have x to the power of 4 plus 3x squared plus 2x plus 1. So when you plug in 1, you have sort of a nice value, right? Sorry, so let me use this. So it's more than 10, right? F of 1.
Now we just take any value greater than f1 and we plug in the value and we expand in that base.
Yes. So like, can you properly write it down? So okay. So tell me how I should write this down then. So I have f of x as, and so on. So
We
I am
first
taking,
compute f1 and take any number greater than f1, call it k, and we ask fk, the value of fk, and whatever we have got the value of fk, we express it in base of f of k.
yes. So how am I expressing it in the base of f of k? That's what I'm asking. So I have got the value of f of k, say. So that is, suppose, m. So now, and now like express it in terms of m, like the decimal, like what you do in case of decimals or binary, like express it in base m.
In base m or in base k?
Like whatever you want,
Base
like
m, base m.
like,
So
like
we
what
take the-
you want fm. I have k, which is f of something greater than f of 1. I have f of k, which is m. Now what do you want to do?
And we
Sir, we find the largest power of k less than equals to m. Like that we check.
Yes, right.
and
So
after
that's-
that we find the remainder and we
So yeah, so
divide
yeah,
the remainder by its largest power dividing and so on.
Wait, I
Yes.
did not understand something. So we
Yeah.
first compute f1 and we take some positive integer k that is greater than f1.
yes,
Right.
yes.
So and then
Why?
we compute
And
f of k.
And you understand why f of 1, right? Because f of 1 is the sum of all the coefficients.
Yeah. And then we take k greater than f of 1 to make sure that it's greater than the greatest coefficient.
Yes.
Then we compute f of k and we get m.
Yes.
So we should just break m in base k, right? I mean, I'm confused in
yeah.
that part.
Yeah. I want the other guys to answer. So I mean, I don't want any hand waving. So I want like what exactly is the value. So you have got m. Now what do you want to do? So Rito brother, tell me. So I have got m. So say suppose m is 1054 and k is 11. Say. So what do I do now?
So should I tell?
We expand 1054 in base 11.
Okay. So tell me like how. So 1054 is equal to what? So I am writing what? So you want me to factorize like in we did for binary operations, like, so what's the highest power? 11 square, right? So I mean, is this like this is something simpler, right? So what is this basically? You don't have to basically write it like 11 square into something and so on. Like it's much simpler. So yeah, Ryan.
Sir, we just divide the number by 11 and then take the remainder alone and then divide the quotient again by 11 and we keep doing that.
Yes, but okay, yeah, that is correct. But like
Yeah, 1054 by 11, we get a quotient and a remainder.
like, but do you see my point? Like when
21.
yeah, I understand your point. That is correct. But well, like if you have f of 1 as 11, what should be the most intuitive choice that you should ask next?
F
Like
of
there
11.
F of
no
11.
no like I can ask something from where I can directly tell you guys the answer. You don't need to even compute these things like the bases. That's what I was saying. So you just
Taking
ask
100, k equal to 100, take.
yes. Why I'm taking 100? Because the value say the okay. So give me a function whose value whose f of 1 is more than 1, more than 10. So for example, this something like this, right? So the value is 12 for f of 1. So if you just compute f of 100, what does it give? Check once. So what's the value when you multiply it with 100?
Basically, there are 8 places. 4 is at the 8th place, 7 is at the 4th place, and 1 is at the 1st place. And
Yes. So essentially, you just have gaps of 3. You just have to check gaps of 3.
yes,
So why is that? Because 100 is basically when you are looking at base 100, you are looking at two numbers at once, three numbers at once. Sorry. Like you can have the function in partitions itself. Okay. So this was with for this one. So try this one. So this is a nice one. So you guys could do this one. So I guess you can also do this one. So try these two. These three actually. Yeah. What is P of 1 and P of minus 1? Just check. And I want you guys to answer this in private chat. Like, don't, yeah, type it down in the chat box. So just compute these two and check what can you say about B.
Okay, sir. I actually have a geometrical view for this.
Yes.
Suppose you have a parabola with ax square, for example.
Okay.
Suppose your parabola ax square, and you take any take any interval on the x-axis with length 2.
Okay.
Now this corresponds to a length interval on the y-axis,
Yes.
right?
Yes.
Like the maximum range between, like,
Yes,
what
yes.
range it covers in the y.
Yes.
So we are trying to find the value, like if the range, if the interval is a minus 1, if the interval is a minus 1 comma a plus 1, then we are trying to find the maximum possible value of f dash a.
Yes. Yes.
Is that legible?
Mm, yeah, yeah, but like, okay. And it also implies something else. So go on.
Yeah, so f dash a, f dash a can go to infinity, right? It can go to infinity.
No, just think
Sir,
about.
oh yeah, sorry, sir, 1 minute. F dash a cannot go to infinity. F dash a, the interval range needs to be between between length of 2,
Yes.
right?
Yes.
So that, like, I think that way I can go forward and solve the problem. Like, it's quite it's relatively easy.
Yes, it's easier. It's much easier. So yeah, you are on the right track, but it's not infinity because the interval length is
Yeah,
fixed.
interval length also increases. So interval length needs to be kept between that. Yeah.
Yes. So yeah, go ahead. You're on the correct track. And if you are and send me the solution in the private chat box, please. And if you're done with that, then I'll tell you to replace the inequality with this. Okay. This
I have already solved for that.
okay.
I have already done for that.
Okay, so nice. Okay, so then do this for this one. So if it was for this one, it was a Putnam question. Okay. So
Yeah, I've seen that before. Like, so if 0, x and 1, you are asking for the leading coefficient, right? Not the uh, middle coefficient.
no, for the middle coefficient. I'm
Then I
asking
have
for
not done. Then I've not done.
this is from a older Putnam, I think like 1960s or something. But yeah, you can try. Like, so just try for this one, and you will understand why this works. And if you want something simpler, just look at what is P1 and P of minus 1. You want to look at B, right? So just try to write B in some other terms.
Yeah, I said it was f dash a, f dash of 0.
Okay. Okay. Yeah, that's also fine. That's also fine. And just let me give you guys one more problem. Like, since this is the last class on number theory, I want to give you guys most of the problems that I can. So if positive integers a, b, c satisfy a square plus b square is equal to c square, then show that there are at least three non-congruent right triangles since you guys wanted some problems on geometry. So this is geometry and Pythagorean triplets both. So at least three non-congruent right triangles with integer sides having hypotenuses all equal to c square. So these are all easier problems than the ones that I have started with today. So I wanted to check whether you guys are actually solving the problems or you know the problems beforehand. So try this and these two and write it down in the chat box. So I'll give you guys 10 minutes, say.
Sir, have you seen the chat?
The maximum value of b should be 4 plus 2a.
Sir? Sir, I have a may have a method for this one. Can you listen?
Yeah. So anyone else with the answer for the previous one? So Ryan gave an answer. So I guess he used calculus for that. So I'll give you a alternate version, alternate solution. So
B less than equal to 4 plus 2a. Can this be answered?
the maximum value of B is 1. So B is this, right? So what is the maximum value of the numerator? So like the maximum that it can take due to this restriction is less than equal to 1, right? So it can be at most 1. It might be 1, but it may not be 1. You need to give an example where it is 1, suppose. So, and if you can give an example where it is 1, then you are done. So what's the best example that you can think of? Right. So this would give you what? So this would satisfy the equation, right? This should, yes, because PA of X is less than equal to 1 for, and we attain the maximum at X equals 1, right? We attain 1. Okay. So since we are talking about techniques, so before we go to other problems, let's solve this one. So because it involves a new technique, for some of you might be. So if positive integers a, b, and c satisfy a square plus b square equals c square, then show that there are at least 3 non-congruent right triangles with integer sides having hypotenuses all equal to c square. So without loss of generality, we can assume A is greater than or equal to B, right? At least. So one side. So the constructions that I want you to see is like, this is not a problem that you can approach if you don't know it, I guess. So the constructions would be this, but if you can play around with this, because there are several things that I'll note down at the end. So right, so this is one triangle. So sorry, this would be C cube. So this is one triangle using the hypotenuse.
The hypotenuse was C cube, not C square.
Yeah, like, yeah, I wrote it wrongly previously. So C cube, yeah. So yeah, that should be a power of 3. So yeah, you will see why. So one more construction can be this. Like, I'll show you the constructions first, and then I'll come to the idea why, how this is helping and why this is helping. So the second construction can be made like this. Right. So this is basically a to the power 4 minus 2a squared b squared plus b to the power of 4 plus 4a squared b squared times c squared, right? So this is essentially a square minus b square c whole square plus 2abc whole square. And the third construction is, let me think, yes, this should be the one, right? So you understand the construction procedure, right? So the powers, let me write down the powers. Yeah. So the most easy way to break this is this, right? Yes. So this should be equal to what? This should be equal to a into a square minus 3b square whole square plus b 3a square minus b square whole square. So I mean, this might be negative, right? But doesn't matter since I'm squaring it up, right? So okay, we can take the modulus in this case. Now, yeah.
Sir, I am saying, okay, but I am saying there's this theorem that the number of, suppose you have a number C.
Yes.
Now, the number of ways that there are two integers a and b such that a square plus b square adds up to c is there is a what?
Yeah. So just look at this. So what you are basically saying is so how I was writing those values. So essentially I was following this sign, sorry. Right. What is cos theta? What is sin theta? So you can write, I think you guys can write this cos n theta and cos sin n theta. You can find values for those, right? Yes. Now one important question. Why are these three triangles not congruent?
Just take the ratio of the sides and see if they are same or not.
Yeah, so give me a easier, I mean, quick argument.
Because
What about the GCD? What about the GCD of the sides of the triangles? There are different powers of C, right? Yeah. There are different powers of C, right? Just check. Right? So that cannot happen, right? The ratio of the sides. That the thing that you are saying, essentially. Right? Yes. The powers of C, this is square, 1, and 0. Right. Okay. So okay, so let's come back here maybe. No. Okay. Okay, so and this one is a nice one. So show that there are infinitely many points on the unit circle such that distance between any two of them is a rational number. So have any one of you seen this before?
sir, I have not seen it before, but I may have a method for it.
Okay, go ahead.
Suppose take the 3, 4, 5 triangle.
We take what?
The 3, 4, 5 triangle.
Okay.
Mark one of the angles, one of the acute angles as phi or theta, whatever. Now the now what I say is that what I claim is that an infinite number of points may be described as one theta, 2 theta, 3 theta, like that.
Okay.
Like up to n theta, like any number theta, any integer multiple of theta.
Okay.
So these are you can find infinitely many points, right?
And these and you will argue.
Sorry.
Okay, continue. Yeah.
Sorry, any even multiple of theta.
Okay. Yeah. Any even multiple of theta.
Any even multiple of theta. So firstly, sine theta is rational, right?
Yes.
Sorry, sine theta by sine 2 theta by 2 is rational, right?
Just a sec.
Yes, same.
Yeah. Yeah. Sine 2 theta by 2 is also rational. Yeah.
Cos 2 theta by 2 is also rational. So
Yes.
any even multiple of 2, any sine of any even multiple of 2 will be rational, right?
Just for the others to be clear, let me write it down what he's saying. So, and so these two, so like let me have okay, so
I am taking theta as 2 of that angle, like pi as 2 of that angle.
okay, I understand what you're saying. So let me just okay, so you're correct, yeah, but for the others to be more clear, let me present it in this way. Like, yeah, 3, 4, 5 is a good triangle to start off with. So okay, let's see. Okay, so suppose this is the xy axis. So now take this triangle like the one he was taking, but I am taking this one so that I can show you the angles quickly. Okay, suppose this is the triangle. So say this is -1, 0. This is 1, 0. So, and this is origin. Suppose so this one be A, this would be now. What he was taking is a right angle triangle, right? So let us also take some points P such that AP square plus BP square is equal to AB square. So I want this to be the hypotenuse and this to be the right angle. Okay. So I'm taking all such points. So those P's, what should be the locus of all such P's? That's a circle, right? That's the unit circle also. So right. Okay. So what should so let this point be some x comma y. So what are the coordinates? So suppose this is some A and this is B. So what should be the coordinates? X should be equal to a square by 2 minus 1, right? And what should be y? Y should be right. So these are both rational, right? So let us take theta as angle BOP. So he was also taking the twice angle. So this is actually twice of angle what? BAP, right? So what is cos theta by 2? Cos theta by 2 is 1 plus a square by 2 minus 1 divided by a, right? And what is sin theta by 2? This is y by a, right? So that is plus minus ab by 2 by a. So both of these are rational, right? Now tell me what you are saying. Continue the argument.
I am saying that any even multiple cos or sine of any even multiple of theta
Yeah.
will also be rational.
Yes. Yes.
Why? Because the expansion sine A cos B plus cos A sine B will continually lead to rational only. There is no a way for irrational to come into the picture.
Yes. Then.
Then other thing is that this theta is not a rational multiple of pi, so it will it will not repeat. Like it will not be such that a theta minus b a 2a theta minus 2b theta is some 2 pi, so that will not
So
happen.
give me a concrete argument from here. Like this you are clear up to this, right? These two are rationals.
Yes.
Now let's take another point, say p dash. Right. So what is pp dash? So this
Actually,
is,
I think my argument is different from yours.
yes, I understand what your argument is, but I am saying like this is just one line, and if you know this, so like I want you to your argument is correct. So you are talking about you took a very specific triangle, right? So that's why since it's clear, I just need infinitely many points. This would also work. But I think what I'm saying is there's a much stronger claim that I can make from here, right? So this is correct. This argument is correct. So like if you take one more point p dash, what is this distance? Can you tell me that in terms of theta? pp dash, since like I mean your solution is correct, but you see my point, right? I want you to know the other solutions also. So what is this pp dash? Suppose p subtends an angle theta and p dash angle subtends an angle theta dash.
You use the Pythagoras formula, right? You take the y and x and y value for both, and it's a calculation.
Yeah, like, but this should be 2 sine theta dash minus theta by 2, right?
Yeah, that is true. You this is what I'm using exactly.
Yes, that's what I am saying. So you are using this only, right? Because you are
Yes.
expanding this into sine and cos.
Yes.
So for any point p dash, this is true, right?
Yes.
So yeah, so then you will use this, right? So sine theta by 2 and cos theta by 2. Now I have already claimed that theta dash by 2, sorry, this is theta dash and this is theta. So similarly, cos theta dash by 2 is also rational, right? So any point on the locus is rational, having rational values. So this minus 2 no, just a sec. I think I messed up the calculation here. This should be what? This should be cos theta by 2 sine theta dash by 2, right? Like this two. So let me clearly write this down. So what I mean is p dash, this is equal to 2 sine theta minus theta dash by 2, right? So this is equal to, and to be more rigorous, let's put this. So this is 2 mod sine theta by 2 cos theta dash by 2 minus cos theta by 2 sine theta dash by 2, right? And this is rational. Yeah. Okay. So just note these two down. If you have any doubts, you can mail me and just give the mock test for 2 days. Like you can submit it later also. So there are many interesting problems there. Then I can give you the solution set. I can upload the solution set then, right? If at least some of you guys try. So let's end the class here today. Fine.
I had a different, like an alternative proposal for this unit circle problem.
Yeah. Go ahead. Yeah.
I was saying that like if we have a unit circle, its radius is 1, so the diameter is supposed to be 2.
Yes.
So if we pick
No,
any
no. Okay. Like you can actually, the size of the circle doesn't matter. You understand, right?
Yes, well, the point I was going to make is that if we take any rational number less than 2, we can have 2 points on the circle whose distance is exactly that rational number lesser than 2. The reason I'm bringing the question of the diameter up is because the maximum distance 2 points can have in a circle is when they're diametrically opposite.
Yes.
So
Yes.
so 2 is going to be the maximum distance. Otherwise, those 2 points will have a chord in between, which will be less than the diameter.
Yes.
Now in that case, we can pick, first of all, we can pick any rational number from not from 0, like greater than 0 up to 2.
Okay.
And secondly, for any such rational number, we can simply place any point on the circle, and like given that rational number, we can point out like that particular point will map to exactly to other points on the circle, which is exactly at a distance of that particular rational number we have chosen, lesser than 2. So for each such point, we can have 2 solutions on the circle which are at a distance of that particular rational number lesser than 2. And we can, since a circle has infinitely many points, we can do this with any point. So for any given rational number lesser than the diameter, obviously, we can have 2 points whose distance is a rational number. Like
I have
distance
also another solution.
Yeah. So this is correct. Yeah.
Consider any 2 points, cos alpha, sin alpha, and cos theta, sin theta. So their distance is coming sine of theta minus alpha by 2.
Okay. Yes.
And so this should be rational. And now we note that in the interval 0 1, there are infinitely many rational numbers.
Yes, essentially that is the same thing. Like I wrote down like the formulas for cos theta by 2 and sin theta by 2. If you write like, so this is called coordinate bash. If you did the same thing in trigonometry, so that would be the values. Yes.
And for those rational numbers, as they're infinitely, and sin theta is onto in that interval 0, 1, so we can take for every rational numbers, we can take sine inverse of that and take and get an angle in 0, pi by 2 for that. Okay. For which sine of taking is that rational value.
Actually, sorry to say, sir, but I could understand neither of the 2 solutions.
No, like I am not understanding this solution, but the previous solution, what he was saying is that given any point on the circle, he can find 2 more points which are having a rational distance.
Okay, if say you find 2 more points, then you also need to find from those 2 more points, you find how many points? 4 points. So the total number of points is 1 plus 2 plus 4, which is 1 plus 2 plus 7, right?
No, I mean he's taking any point and he's generating 2 points, and I think what his construction is, the points are different, right?
The points
Like,
are different, yes.
So for each point he's creating more than 1 point.
Yeah, but okay, suppose you create after you create 3 points, not
Yes.
every point is related, right? Not every point, like suppose you have suppose 2 points have no common ancestor, like suppose you have created 4 points, then how are you saying that every distance between the 4 points is a rational number? Please just construct one, just show me one circle where it works, like put a point.
No, I mean what he's saying is for case 2, I guess, right? Only for 2 points.
Yeah, only for 2 points it is correct, but infinitely many points cannot. It's not correct.
I think he's assuming that if we consider a first point and we take any rational number into
No,
consideration.
what I think your argument was incomplete, but I think it can be completed like this. Like, you have to have the distance between any two of them to be a rational, right?
Yeah.
So, like when you have 1 point on the circle, so you can generate 2 points with a rational distance. That is fine.
Yeah.
Now, there is a construction actually from where you can say that like there's a construction that is very intuitive actually from here, where you can construct 1 point which is actually having rational distance with the all other points. So that was not exactly your construction, but like, do you understand how you should proceed?
I'm sorry to say, sir, no.
Okay, so you start off with a point.
Yeah.
You can pick any point with a any other point with a rational distance. Like, what should be the easiest guess? That should be like
Suppose 1, distance 1.
yes, like, yeah. So the
Diameter is not 1, so no need to worry. Diameter will be diametrically opposite.
not exactly one. Take the diameter was what, 2, right? So divided in the first two Fibonacci numbers in that ratio. So yeah, so that is 1. So like if you continue in a spiral way, so there's one construction that I don't remember right now, so I can give you the construction in the next class, where you can create a spiral.
So in that spiral, every 2 points have rational distance.
Because every 2 point is basically difference of two Fibonacci distances. So so that's how it can be constructed. So it's not an impossible construction, but it's a very difficult construction. So like in the demo lectures I gave, I think, I'm not exactly sure if I gave it there. I think there's one theorem from where you can actually start up with this, but it's a very interesting construction. So I think what he was trying to achieve was that from 2 points. So his construction was only for 2 points. So you need to go from there, and you need to argue that all the distances are rational numbers, right? But
Yeah.
the next solution that I'm not exactly clear about. So I'll ask again, like what I understood, what I think he was saying is that the point x comma y, he was not taking those as x comma y. You can just select, for example, I took a coordinate setup, right? -1 0 1 0. So if instead of a coordinate setup, what if you take ABC and say θ1 and θ2? So then this is 180 minus θ1 θ2. So now you can do the same calculations and argue that these are rational numbers. So is it anything different than that? Ritobrata? So one more solution that I would encourage you to consider was is Pythagorean triplets. So like, I'll just give a hint how you can construct based on this, like and say BP is for UV by U square plus V square, right? So and ABC, if we denote the sides as ABC of the triangle, then I'm saying. Yeah, I denote m as u square and n as v square. Okay, so now think about this, like this will also give you a like understanding why Pythagorean triplets have like there are several problems which use this construction basically, where you can use this construction. So just let me give you an example before signing off. So find all positive integral solutions is 3 to the power x plus 4 to the power y equal to 5 to the power of z. Right? So check mod 8. That's one approach, and Pythagorean triplets is another approach. Okay, so is this fine? So let's end the class here today. Yeah.
All right.
Okay.